Welcome back, everyone. So let's get started with the second part of chapter number 6. So in this video, we will be talking about these three things. We'll discuss the NAT, PAT, CIDR, IPv6, and these kind of concept. So in the part 1, we have already discussed IPv4, and the main agenda item for this video is IPv6, the concept of IPv6, why it is important, and how we can transition from IPv4 to IPv6. So let's get started with the first agenda item, NAT. NAT stands for Network Address Translation. Network address translation. Let's try to understand why it is important, why do we need it, what sort of problem NAT is trying to resolve, and then I'll explain the NAT with this particular example. Okay. So first of all, let's understand. So for example, we have 10 hotels. For example, this is the Hotel 1, which is located in New York. Let's say this is, for example, Hotel 2, which is in Georgia. And for example, another hotel, which is in, for example, Texas. Okay. So we got Hotel 2, and Hotel 3. So we got 3 hotels in different locations. Each hotel has, for example, 3 floors. 1, 2, 3. So each hotel, they got 3 floors. And on each floor, for example, we got 10 rooms. So for room number 1, in the hotel at New York, room number 1, let's say I use the room number 101. I assign this number to this room number. Room number 2, let's say 102. Got it? Now question is, for example, can I use the same numbering here in Georgia? So on the ground floor, can I assign the same number 101 to Georgia's room number, which is located at Georgia on the first floor? The answer is yes. So we can use the same numbering within whatever we have used in the Hotel 1 located in another location. For example, in New York, we can replicate the same numbering model in Georgia and same numbering model at Texas. But within the hotel, we cannot reuse these particular numbers. This is the same idea which NAT will replicate. So the problem, what's the problem? The problem is that the shortage of IP addresses. Shortage of IP addresses. As we know that, for example, if any device want to communicate over internet, a device need to have a specific dedicated IP address. Now, what's the problem? The problem is that with the IPv4, the maximum number of IP addresses which we can generate, as you know, IPv4, the size is 32 bits. The maximum IP address is going to be 2 power 32. This is the number of IP addresses which we can generate. IP addresses. The dedicated, or you can say unique IP addresses. Unique IP addresses. Now, the basic issue is, do you think we have only this number of devices? No. Let's say, let me give you an example. Let's say we have a local area network. For example, this is Google's local area network. Google may have 16,000, or let's say 1.6K computer. For example, we got another local area network at GGC. We may have 10,000 computers. So if you just combine all the local area network, look at all the local area networks. So we will see there might be billions, maybe more than 30 billion, for example, devices. I'm just giving a rough idea. 30 billion devices. So what do you think? Do you think we can generate 30 billion IP addresses? Because each device need an IP address. Now, the problem is we have a shortage of IP addresses. We cannot assign every device a unique IP address. In order to address this issue, NAT came in. NAT resolves this particular problem. Resolve the problem. And what's basically NAT does? NAT, the definition of NAT is it translate, or you can say convert or translate. NAT translate the private IP address into public IP address public IP address into private, and then private IP address into public. Private IP address into public IP address. So this is basically what NAT does. Now let's try to understand this particular definition. Let's try to understand this definition and why it would be easy to manage the things. Now let me just take you guys back. So everybody got it? For example, within the network, you guys can use some numbers and same numbers can be replicated here. I believe this particular strategy will give you some sort of idea. Like the same numbering, like same IP addresses can be used in different locations. That's what NAT is. So let's try to understand with this example. All right, so if you guys see here, these are basically the range of IP addresses. As you know, the private IP addresses which are free. Like these are absolutely free. You don't have to purchase them. These are the free IP addresses. You can design your private local area network by using this. Now, if you look at this example here, I have this, let's say this is my local area network. This is my private local area network. And I have used 10.10.10. For example, 0.0. This is my network ID. Okay. And I have designed this small local area network. So in this local area network, this is my computer 1. I assigned it 10.10.0.1. This is the private IP address of this PC. This PC private IP address is this, and that's for third, and this is for fourth one. Same IP addresses, like say if you have another organization, they can also use the same IP address. Let's say, for example, this is GGC. For example, Kansas State University, they can also use 10.10.0.1. They can also assign IP address 10.10.0.2 to their within their own local area network, like within their LAN. They can use it. So now what's going to happen here? For example, let's say this particular computer and this computer, let's say this one. For example, this particular computer want to access facebook.com. And the IP address of facebook.com is this 50. So the destination IP address is going to be, when they generate a packet, is going to be 50.1.1.1. So, and the source IP address is 10.10.0.2. Got it? Now when this particular packet, this packet will go to the gateway or to the router. And in router, we have enabled the NAT protocol, NAT addressing. Now what's going to happen when this particular packet will get to the router? Router will use this NAT translation table and put this source. What was the private IP address? Private IP address was 10.10.0.2. This particular computer want to access which public IP address? The destination, which is 50.1.1.1. Now, the problem is that this private IP addresses is just within the local area network. Local area network. Internet, they don't recognize that. Private IP addresses, internet don't recognize them. Internet don't know them. They don't recognize these private IP addresses. Now, our organization has purchased this public IP address. This is the public IP address of our organization. So what will happen? The NAT will take this packet and now change this source address, this particular source address with their public IP address. Now the packet, when packet will go here, the source IP address will become 125.12.13.6. So it will be changed with this particular IP address. Destination is going to be the same, like Facebook IP address, FB. The packet will go to this. Now Facebook will see the request came from, for example, this particular IP address. Facebook will generate a response, and this response will look like this. Source is going to be now Facebook, which is 50.1.1.1, and destination is going to be now, destination IP is going to be this one, the public IP address of our organization. This is organization IP address, which is 125.12.13.6. Now they will forward the packet. When the packet will get to our gateway, the gateway will get it. Okay, the response, the source was 50. This. So they will see, okay, this particular packet is for this private IP address. So they will convert it back into the private IP address from public to private again, and then the packet will be delivered back to this computer. So NAT basically what it does, it translate the, or it let you design the internal private network, and you can, all the private IP addresses, all the private IP addresses will be mapped onto this public IP address. Got it? This is basically what NAT does. Now let me just give you an idea about PAT, and then we'll move on to CIDR and the IPv6. Next is PAT. PAT is just an extension of the NAT. PAT stands for Port Address Translation. It's very simple. It has resolved a couple of issues of the NAT. I'm going to give you a brief overview of the PAT and a definition. But if you guys see this particular diagram, where you guys can see here, this is our NAT device, NAT PAT device, where we have implemented NAT and PAT, which translate the private IP address into public and public back into the private. So all these devices, you guys can see all these devices are connected, or this is my private network, and all these devices are connected with a specific port number of my switch. Okay, so for example, if a data travels from this, let's say if this computer want to access any website or send a packet, so this particular packet will get to the router because they are connected with this particular port. So router will translate this IP address 10.0.0.1 with this public IP address and the port number with which that device was connected to. So the packet can be retransmitted to the specific port number. And it will leave the same from the port number specified by the router. Another way to understand this, for example, the same way, like the same example which we saw right here. So for example, if this particular computer is using Facebook, let's say it's also using, let's say, google.com, also watching a video on YouTube. Okay, so video on YouTube. So same computer is basically using different application, Facebook, Google, YouTube. Now, how this particular problem would be addressed by NAT? Because the same IP address, different particular, they're using different public IP addresses. So in that case, what we can do is we can basically assign, let's say, Facebook on port number 1, for example, port number 2, port number 3. And this is the source port number, and we will add the destination port numbers as well, let's say 3 to 1. So we just have to add here another entry, which is port number, the private port number, let's say the same IP address, and the port number 1, this is for Facebook, number 2, the same private IP address for Google, and number 3 for YouTube. Similarly, the same entry would be added, public IP address, the public port numbers, which are Facebook, Google, and the YouTube. So this is the way how PAT can be used. Specifically what it does, so the definition of PAT is going to be, it allows a single public IP address, like this single public IP address assigned to your organization, single public IP address to be used by multiple devices connected to a unique port number. That's a typical definition for port address translation. So basically what it does, it is basically doing the same thing as of NAT, but here what we are doing is each particular device is connected with a specific port, and again with the same example. I mean, this example, which is actual PAT, is like each device can, for example, each device is basically sending out the data with the port number as well. So NAT table is basically also taking care of the port numbers as well. So the data would be, when it would be routed back, it would be routed back to the specific port number to the private IP address. So let's say for data will go to number 1, which is coming from, for example, Facebook, port number 1. Data would route to port 2, which is connected with the google.com. Are you getting my point? So that's basically what PAT is. So let's see what CIDR and then IPv6. Next is CIDR. It stands for classless inter-domain routing. So very importantly, the difference between classless, we will be talking about the difference between classless and classful and what would be the advantage of classless over the classful. So CIDR, there is no concept of classes. Like if you remember in the last video, we have discussed class A, B, C, D and all. So there is no concept of classes. So forget about all the classes, okay, in the CIDR. Here what we use is we basically use blocks. We just use the blocks, and the blocks look like this. The concept is like this. Again, it is IPv4. The IP address is going to be IPv4 with no classes, like no organization of the classes A, B, C, and all. Okay. So here the size or the length of the block is going to be 32-bit, just like the IPv4. And it would be divided into two parts. One is on the left side, it's called block ID, or you can call it the network ID. It represents block ID or the network part or the network ID part. And this particular one is basically for the host ID part or the host part. Okay. Means that the user wants some, again, very importantly to understand in the class, in the classless IP address, what would be the advantage? For example, your client want 1000 IP addresses. So a client want 1000 IP addresses. With the classful IP addresses, we cannot fulfill this requirement. We cannot provide the exact number of IP addresses, We cannot do that. We can assign, for example, let's say if a user wants, let's say 20 IP addresses. Let's say user have 20 computers and user wants 20 IP addresses. So we can assign IP address, let's say 192.168.1.0, for example. Now, as you know, this is a class C IP address in the example of classful IP address, class C IP address. And as you know, this will be the network ID, NID, the network ID. And the last one is 192.168.1.255. This is the broadcast ID. And in between, we can assign the useful IP addresses. Let's say 1 to all the way 254. Got it? So the problem is user only wants 20 IP addresses, and we are basically wasting, we are almost wasting 234 IP addresses. So user doesn't want those 234 IP addresses because user got only 20 clients, 20 computers. How we can fulfill this requirement? So this requirement can be fulfilled with the classless IP addresses, classless, or you can say CIDR, it is classless interdomain routing IP address. The major difference, how you can identify a IP address is a classless or a class 1. You can differentiate it with the notation. So what is the notation? So as you know, the typical IP address is X, like first part, second octet, third octet, and the last octet. So this is the major difference where you will see it would be separated, like you will see the same octet, 8 bits, this 888, and the last one is /n. Now what is this n? So this particular n, what it denotes, it mainly represent, this n represents mask, or you can call it, for example, or you can tell the number of network bits, okay, like reserved for network or network ID part. You can say the bits which are the part of the network, or simply you can say, as you know, in network part, all are basically the number of ones, like how many number of ones would be there. That's another way to look at that. So let me just give you example to better understand this particular concept. Okay, so let's take example. So let me just take example. So for example, we have IP address. Let's take example of 200.10.20.40 and /28. Now everything else was great. We know, we do know that this basically belongs to class C IP address. We know that. But if you see / this, it means it makes it a classless IP address. This is basically CIDR. Got it? So it means there's no class. You cannot say it's a class C IP address. You can't say that because it's basically a classless IP address. So that's a new thing. These 28, it is basically showing there are 28 number of ones, showing 28 number of ones. It means 28, it is the network part or the block ID, network ID bits. Okay. So how you can differentiate? So it is the network ID bit. If you go back and look at the block again, This is the block. So if you see, I have 28, it means the network part. This is the network or block ID 28, and host is 4. So 32 is the total length minus 28. So that is going to be 4. So what does it mean? It means for host ID, so 28 bits are out of 32. 32 is the full, the 32 bits are the size of the IP address, IPv4. 28 bits are reserved for network part, network ID. So we are only left with 4 bits. So number of hosts are going to be, number of possible hosts is equal to 2 power 4, which is equal to 16. It means there would be only 16 possible host in that particular network. Now to better understand that, like for example, you got a question. The question is find out subnet mask, find subnet mask, and find, for example, the network ID of this particular IP address. So your IP address is, let me write it down again. Now the IP address is 200.10.20. For example 40. Okay, this is the IP address. Now question is you need to find out, and again /28. Okay, /28. The question is find out the subnet mask and find out the network ID. So because once we find, because this particular ID, let's say this is your organization, and there would be a network ID, a classless network ID. This is a classless network ID. And for example, this particular IP address belongs to a specific computer, maybe let's say 200.10.20.40. Okay, this is the IP address which is assigned to a computer. So we need to find out the network ID. We need to find out the subnet mask of this particular one. So how could we find out? So as I told you, first of all, I told you guys these are 28 are the number of ones, and again number of ones mean the network ID. So what we're gonna do, I'm gonna actually place number of ones, all number of ones. So if you guys see 8 bits, 8 bits, 8 bits, 8 bits, which makes 32 bits, right? So first I'm gonna, for this one, this is the network ID 1 2 3 4 5 6 7 8 dot network ID 1 2 3 4 5 6 7 8. This is also network part 1 2 3 4 5 6 7 8 dot. Now in the last one there is basically a trick. So how many bits we got? 8 ones. So how many bits we got? 24. And how many network part? 28. So 1 2 3 4. And then remaining are available for host 0 0 0. Remember, the network ID and network bit is represented with 1. Host bits are represented with 0. So I put zeros. So in order to make it, so basically 24 plus 4 from here equal to 28. Got it? Now if you, for example, want to calculate the subnet mask all ones, so you guys know that 1, if you guys, let me zoom it a little, 1 2 4 8 16 32 64 128. If you add them together, all these ones, because these one, so it's going to be 255.255.255 dot. Now let's calculate for this one. You guys know that 1 2 4 8 16 32 64 128. Let's add them together. 128 with 64 with 32 plus 16. Once you add it together, okay, so it's going to be 0 4 2. Okay, 240. So 240, this is basically the subnet mask for this particular IP address. So this is the way how you're gonna calculate the, you can be provided any IP address. Very importantly, look at N, and then you can actually go all the way. I mean, you need to make that number of ones and then calculate the subnet mask. Now to calculate the network ID, very simply, to calculate the network ID, what you're gonna do? If you wanna calculate the network ID, you're gonna write down the IP address like this: 200.10.20.40. And of course 28, we know that. What we're gonna do is we're gonna keep to, this is process is to calculate network ID. If you wanna calculate the network ID, everything else will be same, like 200.10.20. This particular part, we will calculate the binary for that. We're going to calculate the binary for 40. How we will calculate, make 40? So we got 1, 2, 4, 8, 16, 30, 32, 64, 128. Let's make it 40. So 1 and 1 here, and rest are going to be 0, 0. So if you add 32 plus 8, it's going to be 40. So dot, this is the binary for 40. So you just have to calculate the binary for this one, 0, 0, 1, 0, 1, 0, 0, 0. Got it? Now, once you got the binary, again, next, we just calculate the binary, 8 bits here, 8 bits here, 8 bits, this octet 8 bits, and 4 bits, these particular 4 bits are basically the network part, right? So everything else, we don't have to do anything, no changes, nothing like that. All we have to do is, we'll keep the network part as it is, 0, 0, 1, 0. This is basically our host part, right? And this is by, what does it mean? It means this 40 is basically a subnetted value. So we will actually make it all these host part 0, 0, 0, and then calculate the decimal value for this one, decimal for this. So we're gonna put all this value right here, 0, 0, 1, 0, 0, 0, 0, 0. So what would be the network ID if you calculate it? 200.10.20.32. So this is the network ID, and again we need to put 28 as well, network ID for this particular host, for this network. So this is the concept of classless IP addresses. We have learned that what is classless IP address, what does it mean if you have a number on the right side like n, which represents the number of host bits. You just have to put all the ones, we talked about it, and then you can calculate the subnet mask, and you can also calculate the network ID. So please remember, we use the CIDR in order to avoid the wastage of IP addresses. Okay, we use this classless IP. So let's move on to the last topic, IPv6. In IPv6, we will be talking about the structure of IPv6, basic features of IPv6, IPv6, why do we use it, why do we need it, why we need IPv6, and we will also discuss the transition from IPv4 to IPv6. What does it mean? It means, for example, if we have a network or computer working or using IPv4 infrastructure or protocol, how it can communicate with another computer which is using IPv6. We're going to talk about it. Before we start IPv6, you may have a question. The question is, for example, Professor, from IPv4, why we directly jump into IPv6? Why there is nothing like V5? Why there is no IPv5? So the answer is, there was IPv5, which was called Internet Streaming Protocol. It's called Internet Stream Protocol. This particular protocol was not that successful. It was not successful. So that's why we didn't use that. And also it was not used for addressing. So it was not for addressing as well. Like IPv4 and IPv6, these protocols are used for addressing purposes. So IPv5, it was not for addressing. It has some other purposes. We can talk about it in the class. One more thing which you guys need to know, IPv6 is not basically a successor, It's not basically the successor of IPv4. Because if it would be a successor of IPv4, it should be backward compatible. It is not backward compatible. If you want to allow V4 to V6, you need to use some sort of transitions. So it's not basically backward compatible. Other than that, the reason why we need IPv6, the reason is that we are basically running short of the IP addresses. So that's why we actually came up with different ideas, or we use NAT for the transitions and all that kind of stuff, translation of private into public and all that stuff. So we really need some more IP addresses, and that particular need would be satisfied with IPv6. Let me show you how. So in IPv4, as you know, in IPv4, the length of the IP address is 32 bits. And if I just zoom it, you know that IPv4 IP address contains 4 main segments, where each particular segment is of 8 bits, right? So we got the this is 8-bit segment, 8-bit, 8-bit, and that's why we call it octet. And then if you calculate them all, so the size is 32 bits. And the total number of IP addresses which we can generate with IPv4 is 2 power 32. This is the total number of IP addresses. So definitely at some stage in this, as you know, the speed with which we are deploying or designing miniaturized devices like IoTs and all that stuff, this IP address is going to be, I mean, it is already getting saturated, especially in the countries like Asian countries where they have already started working on developing the infrastructure of IPv6. Whereas IPv6, it is of 128 bits. So the length is 128 bits. And here we have 8 segments. 8 segments. If you guys see here, we got 4 octets or 4 segments. And each segment is of 16 bit. 16 bits per segment. Okay. So it's just like this. So we got 8 segments. Each particular segment is of 16 bits. And the total length, if you calculate them all, it's going to be 128 bits. And if I use the same formula to calculate the number of IP addresses, it's going to be 2 power 128, which is equal to approximately 3.4 multiplied by 10 power 38. I mean, it's in trillions. So in next 10, 20 years, 30 years, with the same speed, with the same growing speed of the devices and IoTs, I think it's going to be more than enough. Okay. Now let's talk about a few features of IPv6. So there are a few features of IPv6 which you need to know. So we understood why we need IPv6. We addressed this question. And now we're going to talk about some features of IPv6. The first feature of IPv6, as we have already talked about, IPv6 is 128 bits long. Then within 128 bits, there are 8 segments. We have already talked about 16 bits each segment. It is represented in hexadecimal. Hexadecimal, I'm going to explain you in a bit. The format which we use in order to express the IPv6. It is classless. Like in IPv4, we use A, B, C. Here we have no classes. Then no broadcasting. No broadcast here. No need of NAT. Network address translation, because we have enough IP addresses. Enough IPs to provide, and we can provide a dedicated IP address to any device who is looking for. No backward compatibility. Which is basically a problem, and because of this non-backward compatibility, we use a transition algorithm and transition devices and transition protocol. One is, which is very, very awesome thing of IPv6, it is the auto configuration. Auto configuration means, for example, if your DHCP server, it's not working, it can IPv6 can detect it, and it can, if a machine is trying to access or get the IP address and DHCP server is not reachable, so what can happen, it can assign an IP address using a private IP address. I'll show you in a bit. Okay. Now let's understand it one by one. Now we know that the segment, we talked about this particular segment, like this is how it will look like. We'll see that how exactly it can be presented. But before we see how we can represent our IPv6, we need to understand the hexadecimal representation. That's very important. So for hexadecimal representation, I'm going to actually show you a small table here, which is hexadecimal to binary conversion, which most of you guys are already familiar with. So first of all, in hexadecimal, as we know, as most of you guys know, we write it into 4 bits. So like each particular bit, or you can say entity, is represented with 4 bits, like four bits, or you can say half or nibble, or you can say half byte. So total number of values, or total number of you can say the values we can represent is 2 power 4 is 16. Okay. So how we can do that, what's the process and things like that. Let me just draw a small table for you guys. So let's say this is the decimal values. The decimal values which we can understand: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we got 16 bits here, you guys can see. And the hexadecimal representation of all these. So let me hexadecimal. It's 0 will be 0, 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not 10, sorry. So 10 is represented as A. We start A. 11 is B, 12 is C, 13 is D, 14 is E, and 15 is represented as F. Okay, this is basically up till now where we go. Now, as I told you guys, each particular entity is represented with 4 bits in binary. If you convert into binary, so what's going to happen? 4 bits, like what we will do is 1, 2, 4, 8 up till here will go. Like you remember 2 power 0, 2 power 1, 2 power 2, 2 power 3. So I'll go up till here. So I want to make zeros, so everything would be 0, 0, 0. So binary for 0 is going to be 0, 0, 0. Binary for 1, we need to make this thing 1, right? In order to make it 1. So 0, 0, 0, 1 is going to be 1. 2 is going to be 0, 0, 1, 0. 3 is going to be 0, 0, 1, 1. And then I want to make 4, so 0, 1, 0, 0. 5 is 0, 1, 0, 1. 6 is 4, 2, so it's going to be 0, 1, 1, 0. 7, 0, 1, 1, 1. 8, it's going to be 1, 0, 0, 0. 9 is going to be 1, 0, 0, 1. 10, which is A. 10, I need to make 10, so 8 plus 2. 1, 0, 1, 0. B is 11. 11 is 1, 0, 1, 1. Then I need to make 12. So 8 plus 4 is 12. So it would be 1, 1, 0, 0. 13. 8 plus 4 plus 1. So 1, 1, 0, 1. 14, 1. 12, 14, 1, 1, 1, 0. Last is F, all 1, 1, 1. So this is basically how we can convert. I mean, the hexadecimal can be represented in binaries, and you guys can see all this table. Now we can use this particular table in order to convert the values. Like for example, if you are given a hexadecimal number, how you can convert it into binary. So let's say, for example, you are given a hexadecimal value, let's say 26AB. For example, this is the value given to you. Now, first of all, you know that the number is given by 26 for AB. You know, AB are typically used to express the hexadecimal. So if you want to convert the binary, so what would be the binary for 2? The binary for 2 is 0, 0, 1, 0, 0, 1, 0. Okay. And 6, this is 6, 0, 1, 1, 0. For each particular bit would be represented in 4 if it is an hexadecimal. A would be represented, this is A, 1, 0, 1, 0. B is going to be 1, 0, 1, 1. So this is basically the way how hexadecimal can be represented in the form of binary. You can also be given a binary and you can convert it into hexadecimal. For example, let's pick a random number. Let's say you are given 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, for example. So what we're going to do is, this is the binary and you have been asked to convert this binary into a hexadecimal. How are you going to do it? So what we will do is, we will make it in segment of 4 bits. Okay. That's for exact. I mean, I didn't expect that it's going to be that exact, but that's fine. Okay, so that's great. So 1, 1, 0, 0. So what we're going to do is, we need to find out what would be this is the binary, what would be the hexadecimal value. 1, 1, 0, 0. So 1, 1, 0, 0 is C. 1, 0, 0, 0. 1, 0, 0, 0 is 8. 1, 0, 1, 1. 1, 0, 1, 0, 1, 1 is B. 1, 0, 0, 1. 1, 0, 0, 1 is 9. So hexadecimal number is going to be 9B8C for this particular binary. So I hope you guys got it. You might already know that, but I just want to make sure that everybody knows that how to represent a hexadecimal number, because IPv6 mainly use hexadecimal for representation. Okay, so let's see how IPv6 IP address looks like. And there are some certain rules that I'm going to actually explain you a few rules here to express a hexadecimal IPv6. So IPv6 could be something like that. Let's say this is a IP address FFFF, typically separated by this colon. Okay, then A890, for example. Then CD AE. Then for example we got 0000 0000. Let's say AE02. For example FFF. Let's say A123. Okay, now if you guys see here, we got 8 segment 1 2 3 4 5 6 7 8. 8 segments, right? Each particular segment is of 16 bits. How 16 bit? Because this is hexadecimal value, and each hexadecimal value represent 4 bits, right? 4 bits. So each hexadecimal value represent 4 bits. This is 16-bit segment, and total, if you calculate it, it is going to be 128 bits. This is how a typical IP address IPv6 look like. Now, there are basically certain rules. Again, our book has not discussed those rules in detail, but I'm going to actually quickly tell you those with some example. So, for example, this is your this is the IP address given to you, and you have been asked to, for example, shortest, like abbreviate this IP address. Abbreviate this IP address. Abbreviation mean like you need to actually make it short. How you can truncate few values. So for example, if you see the zeros, all zeros are showing up in a contiguous fashion. Okay, you can actually replace it with the double colon. It's not only 2, there can be 3, for example. Let's say this IP address could be shown in a short form like FFF A890 CD AE, and then I see there are continuation of 2 or more blocks. There are 2 blocks, so I'm going to actually put this thing AE02 FFFF A123. Now you may ask a question, Professor, you were saying there should be 8 segments. But right now, I mean, in this IP address, we are less than 8 segments, but we know that 1, 2, 3, 4, 5, 6 segments. So this basically represent there are 2 segments having all zeros, right? There is another example just to clear the doubt. For example, let's say the IP address was FFFF, and then let's say A890. For example, let's say CDEA. For example, 1, 2, 3, 4 zeros, 1, 2, 3, 4 zeros. 1, 2, 3, 4 zeros. Let's say we got this thing, FFF, and let's say AE123. Then how are you going to represent it? Very simple, the same strategy. It's going to be FFF A890 CDEA, and this is the continuation. So there would be 4. We'll skip that. We'll replace it with this, just one segment like this column, and then FFF AE123. This is the IP address short form. So no matters how many are there, you will replace them with this double colon. Another way to shorten them, for example, there is another example. Let's say, for example, let me just take this example of this one. For example, if this particular IP address, IP address was something like, let's say, this was, for example, 0890. This is, let's say, 0D something. So how you can do that? So it's going to be FFF. If, for example, 0 is on the left side, then we can skip it. So it's going to be 890 0. So we're going to DEA, then double colon FFF AE123. Got it? So if you guys see, I mean, we know that you may ask a question, Professor, there are 3 values. I mean, there's supposed to be four you can say the 4 values. Typically there should be 4 values right here. So it's kind of obvious, like on the left side, there would be zeros. And for example, let's say if we have zeros on the left side, 0000, 0000, let's say this is sort of IP address. Okay, 1, 2, 3, 4, 5, 6, 7, And let's say, for example, one, let's say we have ABC here, ABCD. How we would represent it? All zeros, so we can actually do, because all these are in a continuation, so it's going to be represented with double colon ABCD. That's it. Okay, so this is basically the way how these IP addresses are typically can be represented. A few more things. I'm gonna quickly tell you a few addresses here, a few IP addresses which you need to know about the IPv6. There is also a loopback address. If you remember the loopback address, remember the one in the IPv4, it was 127.0.0.0, the whole domain, the whole range, sorry, the whole range was dedicated for the loopback, right? Here in IPv, this is IPv4. In IPv6, the range is 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 1. So this is basically loopback. As I told you guys, I mean, this zero, I mean, you may ask a question why it's not represented in the way. I mean, it can also be represented, it's a shorter form, 0, 0, 0. Okay, 0, 0, 0, 0, right? 0, 0, 0, 0. 0, 0, 0, 0. I mean, this is another way to represent it. 1, 2, 3, 4, 5, 6, 7, and here is going to be like this. Okay, so all these zeros straight away, so you can do this. And on the left side zeros, you know that we can represent with 1. So this is also basically IPv6 loopback. It's called loopback address for IPv6. Okay. Other addresses are, it's typically like this. We typically show, I mean, if you want to write a loopback, so we typically write it like this, 128 bits. So what does it mean? It means all the 128 bits are reserved for network, or privately you can use it. Okay. Okay, so here we got 7 segments. Another one is, for example, if you want to map a IPv6 to IPv4, let's say IPv6 need to be mapped on. So we use a generic IP address where we have these double colon FFF. So it composed of 6 segments, okay? Then we will have 0 here, 0 here. This is an 96. So what does it mean? It means 96 bits are reserved for network and remaining 32 bits are for the host. Got it? I'm going to explain you guys. This is basically called mapping IP address. Mapping IP address. Okay. Other than that, there is another one which is basically called link local address. Link local address in IPv6, important to remember it. It starts with FE80, and then colon with 10, which is representing the network ID. So what exactly this represent, and what is the local link IP address? It's also called APIPA. What is APIPA? Automatic private IP addresses, automatic private IP addressing. Okay, this is APIA. So automatic private IP addressing. Okay, so when do we use it? Remember, I told you guys IPv6 is basically, it performs auto configuration. So for example, if DHCP is unreachable, let's say if DHCP server, dynamic host configuration protocol server, is down, if this particular server is down, who is going to assign the IP address then? Then what happens? System will automatically get this sort of IP address. Like IP address will start from here and then it will get the other values. Okay, so by default it will get the values. This is called the local link address, but that particular address will not use globally. It is typically used internally, not globally, internally, just like a private IP address, if you guys remember that one. Now let me just quickly show you one thing here, and then I'll quickly show you a transition methodology, how we can do the transition. I'm going to quickly show you how we can use this particular IP address to convert it into IPv4. How we can convert IPv4 address. You're given IPv4 address. How you can convert into IPv6 manually. So this is the IP address, the IPv6 fixed IP address. This is fixed, by the way. It's a fixed address. If you want to map IPv4 onto IPv6. What does it mean? It means if you want to convert an IPv4 into IPv6, this is going to be a fixed format that you use. So if you guys see here, first of all, we need to write down, this is a short form of IP address. We're going to make it big. How we can do that? You guys can see here 1, 2, 3 segments. So there should be 5 segments on the left side, which would be 0, 0, 0. So 1, 2, 3, 4. Okay. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Right. And now this is going to be 6 segment F, 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 F. And this is again all zeros. As you know, we can compress it to 1. 1, 2, 3, 4. 1, 2, 3, 4. So you guys can see here we got 128 bits. Like each particular one represent 8. One represent 8 bits. So sorry, 4 bits. My bad. 4 bits. And this is basically the whole address is 16 bits. Right. The whole, if you guys calculate that whole segment, I'm sorry about that, the whole segment is 16-bit, so the total length is going to be 128-bit. So if you calculate, this is 16-bit, 16, 16, 16, 16, right? And this is also 16. So this particular part is basically used for network. So we got 6 segments reserved for the network part, network ID, so which is a 96 bits. You can calculate 16, 16, 16, 16, 16, 16. If you add them together, all these 16, it's going to give you the answer 96. So the left one is 32 bits, which is for IPv4. And you know that IPv4 address is 32-bit. Makes sense? And here, if you guys see, all the 5 segments are 0, and this particular segment is all 1. Got it? Now, how we can calculate IPv4, convert IPv4 into IPv6. Let's say, for example, this is the IP address. You got an IP address, for example, let's say 192.168. For example, 10.28. Let's take that. We need to convert it into IPv6. How we will do it? First of all, we will calculate the binary. The first step is calculate binary. We'll calculate the binary for 192. We need to calculate the binary of 192. So how we can do that? I mean, you can write down the table, and you can do that way as well, like the same way 1, 2, 4. I mean, all that. I mean, you can use this one as well, this particular table. Okay, you can use this particular table to calculate the binaries, but again, this table is not enough for that. So what we can do is we can calculate it 192. So we can actually make it like 1, 2, 4, 8, 16, 32, and all that. So we'll use the same strategy. So 192 binary is 1, 1, then 2, 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and 168, it's gonna be 1, 0, 1, 0, 1, 0, 0, 0. So 1, 2, 3, 4, 5, 6, 7, 8. All right, 10. So it's going to be 0, 0, 0, 0, 4 zeros, 1, 0, 1, 0. Got it. Then we're going to make 28. It's going to be 0, 0, 0, 1, 1, 1, 0, 0. So if you guys calculate it, you'll find this particular binary for this IP address, right? So now what we gonna do next, we will actually convert, because as you know, hexadecimal is 4 bits. So we will split it into 4 bit segments. Right? And for this particular segment, we're going to write down its hexadecimal value. So second step is we split it into 4 bit segments and then convert into hexadecimal. This is the third step. So 1100, if you guys check it out, 1100 is C. So 1100 is C. 000 is of course 0. 1010, it's A. 1000 is 8. 000 is 0. 1010 is again the same A. 00001 is 1. 11000 is C. So the hexadecimal value is gonna be, will combine the four C0A8, okay, and then for this one is gonna be 0A1C, and now we're gonna put this value down here. So the overall segment is gonna look like, so 1 2 3 4 zeros, 1 2 3 4 zeros, 1 2 3 4, 1 2 3 4, 1 2 3 4, okay, and then F, then C0, like this particular value will put here, C0A8, and then 0A1C. Got it? If you want to make it short, so you can actually put like all zeros would be replaced with this, as you know, will replace because it is straight zeros. F, C0A8, and then 0A1C. This is basically the IPv6 for this particular IP address. Okay. I hope you guys got it. If you will have any other questions, problems, we can do more examples as well. But please do watch this particular segment again if you will have any question. Now let's move on to the last agenda item, which is basically how we can do the transition. Like how, for example, two computers or two networks, let's say this network is on IPv4, and let's say it want to talk to another network which is on IPv6. Like this computer is on IPv4 and this computer is on IPv6. How they can talk to each other? What is there any process each time we need to do that, tunneling, we need to do this sort of mapping? If we have a IPv6, how we can convert this IPv6 into IPv4? How IPv4 is converted, I've shown you guys this IPv4 converted into IPv6. How IPv6 can be converted into that. So let's see that how IPv6 can be converted into IPv4. There are plenty of methods to do that. How you can make them bidirectional communicationable. So this is called transition methods. Transition methods. For the transition methods, there are plenty of ways to do that. One of the method is dual stack router. Second method is tunneling. Okay. In dual stack method, because all your computers, all the modern computers, so dual stack router, all the modern computers, they basically come with both of the systems. Like for example, if you have this is your computer, it does have a IPv4 infrastructure. It does have a IPv6 infrastructure as well. And let's say if your computer wants to communicate, or you want to go to google.com. So you just type here google.com. This particular request will go to the DNS server. DNS server will resolve this IP address. And for example, if this IP address was, let's say IPv4, then your computer will use this infrastructure and get to the destination. All the routers, modern routers, switches, they also support the same thing. If, for example, the reply comes, it is IPv6, then what's going to happen? Your computer will use IPv6 infrastructure and get to the destination. But what exactly happens inside it? Okay. For that particular purpose, we use mainly tunneling. And one of the method is trade-off tunneling. That's the method. So one of the largely used transition method is trade-off tunneling, where what happens, for example, let's say we have a device or a computer or a network which is operating at IPv4 and it wants to communicate with IPv6. The problem is this device cannot directly communicate, so we need to put some sort of transition in between. What transition, how we do that? So there are basically trade-off servers, tunneling servers. What they do is they basically encapsulate IPv6 packets within IPv4 packets. So what happens? So we call them basically, it is IPv4 to IPv6 tunneling. Okay. What it does, it encapsulate IPv6 packets within IPv4. So let me just try to explain you guys how exactly it looks like. So for example, when the packet will go to Trado server, so this packet, which is IPv4 packet, the packet will go to Trado server, and that packet would be of 32 bits. When it will be passed through the Trado server, get to the IPv6, it will become of 128 bits, which is basically IPv6, compatible with that particular network. It's gonna do? It will basically, when it will get to the Trado server will have this 128-bit chunk, and at the start of the chunk, which is basically the prefix, the address starts with the, which is called prefix. It starts with a 2001, goes all the way to 000, which is 32-bit. The next is basically the IPv4 of Trado server address. This is 32-bit. The Trado server IPv4 address, which will be something like WXYZ, whatever the IP address, IPv4 address is going to be. Next, the 16 bits are different type of flags. Okay, this is 16 bits of different flags, which is like, of course, one chunk, one segment. The next 16 bits are basically reserved for UDP port, and the last one is basically the 32 bits, which is reserved for client public IP address, IPv4 address. So here we will have WXYZ, whatever the client's 32-bit IP address, it will directly go down here. And these are basically the extra things which Trado server is going to put. And now this particular message is a 128-bit and encapsulated form of IPv6. So this is the IPv4, which is encapsulated inside IPv6, and that's what the Trado server, the tunneling, it exactly does. There are some more details about it which we will discuss in the class. We'll discuss everything in the class. If you will have any questions after you watch the video, you guys can bring it up in the class. See you all.